Uh, okay, Ramiro, let's start today's class. So right now we are in the week 8 of this particular course on Introduction to Material Science Engineering, where these are the list of the content that has been covered. I hope you are asking for this only. These are the content which you are asking for that. What and all the list of the content that has been covered in this particular week 8. Okay, can you please clarify? I not got them. Previous lecture. Okay, previous lecture means previous doubt solving sessions. Uh, you can always unmute yourself. I will be great.
Good afternoon, sir. I was
Yeah.
asking about the content you usually show us in the problem solving sessions.
Okay, so you want for the previous week,
Actually,
week
have
7.
posted up to week 5, I think. Week 6 and 7 are not available yet.
Oh, oh, that one. Actually,
Yeah.
I will upload it by today, so
Okay,
you can see
sure,
it.
sir. Thank you.
Yeah. And meanwhile, I will give you the video link, so you can go through those videos like which we recorded.
Yes, sir. I had gone through the videos. I just wanted to download the content.
Okay, sure. We'll do it today. It won't be in the PPT because I was far. I was not in the my lab, so I made it on the paper. So I will click the pic.
Sure, sir.
I will upload those things in the link which you have given.
Okay, sir. Thank you.
Yeah, yeah, great. Okay, let's start. So in this particular week, the list of the content that has been covered are the we discuss about the eutectic, eutectoid, and hypereutectoid. Sorry, eutectoid, hypoeutectoid, and hypereutectoid steels. We discussed the microstructure of each of them. First, we discussed about the eutectoid, which is mostly pearlite in nature. We saw that only the pearlite microstructure is there. Then we went to the hypoeutectoid, where we saw that there will be some ferrite and pearlite combinations are there, mixture are there. Hypereutectide is cementite and pearlite. Those things we have saw. We also saw that at what different temperature, how the microstructure evolution will take place. Whether the microstructure will form first as the grain boundary or inside the grain. Those things we have discussed. Then after that, we discussed that diffusion. Regarding the diffusion, we discussed. For example, introduction, we discussed that like fixed first law, fixed second law, and so on and so forth. We discussed those things. Then the error, which is the error function, we discussed in the fixed first law. Atomic mechanism of the diffusion, substitution and diffusion we discussed, and diffusion path like the grain bond diffusion, lattice diffusion, surface diffusion. Those things has been discussed. We discussed about the steady and unsteady state, that confusion which is already been there, which is always there, that second like fixed second law is not steady state, which is not true. Okay. So these are the list of the content that has been covered. So if in this particular content, if you have any doubt, you can let me know. If not, we'll move ahead. Okay. Since there is no doubt, let's move to the question number 1. The question says that which of the following is not an invariant reaction in the iron carbon system? Martin-Side transformation. That's yeah, very good. Because remaining all the things we have saw, like at very high temperature, peritectic reaction take place. At lower temperature comparatively, it will the like more than the 2 weight % carbon. There we have saw that eutectic reaction take place, where the cast iron is there. And then the eutectoid reaction takes place at 725 degrees Celsius, approximately like that, at that temperature. Martin-Schiff transformation is like it's not a equilibrium transformation, and so it is not shown in the equilibrium phase diagram. Okay, very good. Let's go to the next question. Question number 2. What is the microstructure of a slowly cooled eutectide stream? Ferrite, cementite, perlite, or austenite? Slowly cooled eutectoid. Eutectoid means 0.08% carbon. So we have this is a 0.8%, this is gamma, and this is 0.8% carbon. So here we are slowly cooling it. What we will get? We know that there won't be any C perlite. Very good. We won't get any proeutectoid, ferrite, or cementite, which we will get mostly in the hypo. Hyper we get proeutectoid cementite. Here we get proeutectoid ferrite. At exactly 0.8% carbon, we won't get those things. We will directly get the perlite. So 100% perlite will form at 0.8% carbon. Very good. Let's move ahead to the next question, question number 3. Now here, we have to do the fill in the blanks. The iron carbon system contains three invariant reactions. What are those? We have studied that there is a total three invariant reactions take place: eutectic, eutectoid, and peritectic. Perfect. Eutectic take place, eutectoid take place, and peritectic take place. Okay. Just for the sake of completeness, I will write peritectic. The eutectoid reaction occur at dash temperature in the iron carbon phase diagram. So we are focusing about the eutectoid. At what temperature this reaction will take place? Again, we have to write in the degree Celsius only, that is 725. That's right. If in the some exam it was written that 727 or 7 somewhere near to that, please go ahead with that because this is not very exact value. From one book to another, it will keep on varying. Now, perlite is a mixture of that and that space. So perlite we know it's a mixture. It's a laminar mixture of two phases. We call perlite to be the micro constituent. This perlite is made up of the two phases. Which are those two phases? That is what they are asking. So they are mostly the ferrite and cementite. Yeah, that's perfect. Right. So we can write ferrite and cementite. Now, second, the last one. In the phase diagram, steel with the carbon content less than zero point 0.8 are called dash steel. It's very easy. Hypoelectric. Perfect. So with that, we have solved this question number 3. Let's move ahead. Let's go to the question number 4. It's a match the pair. So first one, that is the hypoelectric steel. First one is going to match with the B. Perfect, right? 0.8% carbon. Second one is going to match with the hypoelectrite. So it is C. That's correct. Hypoelectrite will match with the, you can say option D. Very good. And perlite is a mixture of ferrite and cementite, which we have learned. And austenite is very easy that the only one is left. So it is comparatively, compared to the ferrite and the remaining thing, it is a high temperature phase. Will match with the A. Very good, Rami Reddy. So let's go with the next question now. Question number 5. So question 5 says, in a hypoelectric steel, the first phase to form upon cooling from the austenite phase field is what? Talking about the hypoelectric, that is, it is less than 0.8% carbon. So which one will be the first phase that will form? No, it won't be the perlite. Perlite will form in 0.8%, exact 8%. So see, let's take a phase diagram. Here we have austenite. Here we have alpha ferrite. Here we are getting, just now we have discussed that we'll get perlite, that is uh, it's a mixture of alpha ferrite, alpha iron, and Fe3C. In between them, it will be the gamma, that is austenite plus ferrite. Here it will be the austenite plus cementite. Again, now we have to see that we are talking about the hyperheteroid steel, that is, we are in this particular region. Let's take any of the composition. Okay, so what we are telling that this is point 0.8. We're taking any composition, let us say point 0.4. So now, in a hyperheteroid state, the first phase to form upon cooling from the austenite phase. So this is the austenite phase. This all are the austenite phase. So this here it is austenite, here it is austenite, here it is austenite. Now here, once we cross this particular line, what we are getting? Along with the austenite, we are getting the ferrite. So the first phase to form in the hyperheteroid steel is a ferrite. After that, once this ferrite will be formed and the composition of the austenite changes within the microstructure changes to point 0.8, then the pearlite will form. Clear? Similarly, if someone asks you what would be the first phase to form for the hypereutectoid, then in that case, what we will answer? Let's say we are in this particular region. In that case, answer will be among this, which one will be the one? What do you think, Rami Reddy? That will be the option A. Perfect. Okay. So the hyper we got to know. Hyper we got to know. What about the eutectoid? Which one will the first phase will form after we cool from the austenite? Among this, which one will be the right answer? What do you think? Answer B will be the right answer. So this is, we can say, for the eutectoid. This will form first will for the hyper, and this one will form for the hypo. Martensite will form when we do the rapid cooling. So with that, we have solved the question number 5. If there is any doubt in this, please let me know. If not, let's move ahead. Let's go to the next question, question number 6. Now, where does the alpha phase preferentially nucleate during the cooling of the hypereutectoid state? So we just talk about the hypereutectoid state and we talk about its cooling process. From the austenite, it is cooling. Now they are asking that where this alpha phase, which is formed, which we talked that okay, this one is going to form, where it will nucleate. Option B, at the grain boundary of the austenite. That's right. Okay, within the austenite grain, no. Why it is going toward the grain boundary? The reason is that the grain boundary is always at the higher energy state compared to the grain, and their structure is also very distorted at the grain boundary. So it is very easy for any new phase to reappear onto the grain boundary due to the high energy. So they will provide sufficient amount of energy for the nucleation site to occur. Okay, they will act as a nucleating site. And on those nucleating site, which is having the higher energy, it is very easy for the new upcoming phase to appear. And that's why it will be the grain boundary of the austenite. Randomly throughout the structure? No. At the defect inside the cementite. Inside the cementite, they are talking about no. Cementite is not there. Let's say instead of cementite, they talk about the austenite. In that case, this can be the right answer, but the grain boundary will prefer. Okay. So for example, one can say in a grain, let us say this is my microstructure where the austenite is there. I started cooling. So what I got? Okay, here the ferrite will start forming. This will be the ferrite phase. Now let us say some inside them there is a dislocation. Now dislocation is also a defect. So it will also be the additional of the energy. The energy will be the energy of the system will be again enhanced. So here also the nucleating site will occur. Here also they will nucleate. But the grain boundary will be preferred more. Grain boundary is more distorted compared to the one single dislocation. Okay. So among these two, we'll prefer this. But if in your question, if in your exam the questions are MSQ, then in that case you will select B and D, both the cases. Okay. So with that we have solved this question, question number 6. Let's move ahead. Let's go to the next question. Yeah, yeah. True and false, right? So a hypoelectric steel contain more than 0.8% carbon. So what do you think? It's a false. Very good. Perlite consists of a alternating layer of the ferrite and cementite. Is it true or false? Perlite. It's true. Perfect. Next question. The proeutectide phase in the hypoeutectide steel form after the eutectide reaction. Is it true? The proeutectide phase. This is false. Proeutectide phase, we got to know that it is alpha ferrite. Alpha iron. And it will form before, not the after. It will form before the eutectide reaction takes place. D. The eutectide reaction occur when the liquid phase transform into the two solid phase. False, right? Right? They are telling that a liquid is there. It is transforming to the ferrite, that is S1 alpha and beta. And this is a eutectoid reaction. We know that it is not the case. This is a eutectic reaction, not the eutectoid. So it is a false. Now the last one. The amount of pro-eutectoid ferrite decreases as the carbon content of the hypo-eutectoid steel increases. So what do you think? What is your opinion on this? The amount of pro-eutectoid ferrite decreases as the carbon content of the hypo-eutectoid steel increases. So you're telling it's true. Yeah, because that lever rule we can say. From the lever rule we'll get that it will decrease only. Perfect. So again, this is the true. So with that, we solve this question number 7. Let's go to the next question. Question number 8. The final microstructure. Yeah, the final microstructure of the hypereutectoid steel consists of. So among this, the final microstructure will consist of what for the hypereutectoid steel? Ferrite perlite, austenite ferrite, perlite, prototype cementite, only cementite. What do you think? A, B, C, or D? Right. It will be the C. We know the ferrite perlite will be there, and some cementite which have already formed. Along the grain boundary, the cementite will form, and inside them there will be the network of ferrite and cementite. That is perlite. So this is how the things will be. They specified that this is a pro-eutectile ferrite. So even if someone not wrote pro-eutectile, if they are only writing perlite and cementite, then two answer will be the right. Writing pro-eutectile means that they are providing additional information, which is good. Okay, let's move ahead. Let's go to the question number 9. What is the primary driving force for the carbon diffusion in the steel during the carbonization? Carbonization is a process where we diffuse the carbon within the steel to increase its strength, to increase its hardness. So, what is the primary driving force for the carbon diffusion? Is it the temperature, pressure, electric field, magnetic field? Very good. It's a temperature. During carbonization, we are not talking about the pressure difference, neither the electric field nor the magnetic. Let's move ahead. Which of the following is an advantages of using the low carbon steel for gear making? Low carbon steel for gear making. So we need to find the what are the advantage low carbon steel provide. Higher hardness, low wear resistance, better machinability, higher cost, better machinability. Very good. Higher hardness, it won't be there. If we decrease the carbon, ductility will increase. Low wear resistance, sure, it will be having the lower wear resistance, but it is not the advantage, right? This is disadvantage. Only this one is the factor. Higher cost is never an advantage. It's a disadvantage. Okay, let's move ahead. Fix first law of diffusion state that the mass plus is proportional to temperature gradient, concentration gradient, electric potential gradient, or pressure gradient. What do you think? So we are talking about the mass plus, whether it will depend upon the temperature, concentration. Since we are talking about the mass will see if we put a perfume in one corner of the room, it will diffuse to the another corner because the concentration in the mass is there. One side there is a high concentration, other side is a low concentration. So the mass plus this flux, it will depend upon the concentration of the gradient, concentration gradient. Perfect. The diffusion coefficient D is highly dependent upon. See, it will depend upon all the factors which we have noted, but the high dependency on which of the factor they are asking. So we have so that D equal to D naught exponential minus of Q upon RT or KT. So here we have seen that the temperature is a major factor over here. So among all of this, the temperature is the factor on which the diffusion coefficient will depend to a larger extent. Let's go to the next question, question number 13. What does Fick's second law describe? So here we are talking about the Fick's second law. So the relation between the flux and the concentration gradient. Think whether it's the first or second, whether whether the option A is described by the Fick's first law or Fick's second law. Let's go to the next one, the relation between the rate of change of concentration and the spatial change of the flux. We have shown that in the Fick's second law that dc over dt, rate of change of concentration, is depending upon the dc over dx, second differential of the second spatial differential of the concentration. So the first differentiation of the concentration with respect to the time, that is the rate of change of concentration, depend upon the second differential of the concentration in the space. So the option B is the right answer. Let's go to the option C, the diffusion coefficient dependency on the temperature. No, it's not the case. The effect of the pressure on the diffusion? No, we will not consider the pressure effect. The relation between the flux and the concentration gradient, that is J equal to minus of D dc over dx. This is the first law, not the second law. So our right answer is option B. Okay. If any doubt, let me know. If not, let's move ahead. Let's go to the next question. Question number 14. The second law is derived using which fundamental principle? What do you think? Please let me know your answer. That on what basis Fick's second law has been derived? Which principle has been used to derive the Fick's second law? We have saw in the class that the Fick's second law is mostly based upon the concentration, like the conservation of the mass, right? So it's not the first law of thermodynamics, it's not the conservation of the momentum, it's incorrect. Only the right answer is option B. So the conservation of the mass is the one which will lead to the formation of the Fick's second law. Let's go to the question number 15. Substitutional diffusion primarily occur through. So now we are talking about the substitutional diffusion. What is substitutional diffusion is? Oh yeah, that's right. It's a vacancy mechanism. So 15 will be the vacancy mechanism. Ring mechanism is required high activation energy, that's why it's not feasible. And diffusion through the grain boundary. No, it's not. See, this is a feasible diffusion mechanism, but it's not the substitution. And direct interchange mechanism, they're talking, okay, A is there, B is there, they will interchange. This is even complicated than the ring mechanism. So only the right answer is option B. Let's move ahead. Let's go to the question number 16. In substitutional diffusion, the presence of dash is essential for the atomic moment. Yeah, again option B. Vacancy is the one which is required over here. So we'll say that the vacancy in the substitution. So more or less 15 and question number 15 and question number 16 were exactly same. Now let's try to solve this numerical. The numerical is saying that the diffusion coefficient for the copper in aluminum at 500 and 600 are given to us. So they are talking about the two temperature. That is, one temperature is 500, another one is 600. The unit is degree Celsius. So their diffusion coefficient is given to us. This is given and this is given. Determine the approximately time. Determine the approximate time at 500. So they are talking about the time. At 500 we have to find. That will produce the same diffusion result at 10-hour treatment in the 600. So in 600 they give the treatment for the 10 hour. Now our industry want to produce the same result which they produce at 600 degrees Celsius for 10 hours in the 500 degrees at the 500 degrees Celsius. So how much time they should heat? They should heat. See, after solving the fixed second law, we got to know that it will depend upon A plus B and error function, which is x upon 2 root dt. Right. See, they want to produce the same concentration, same result. So this is fixed. Right hand side is fixed. Left hand side A and B, they are the constant. And since we are talking for the same material, so A and B will remain same. So our entire thing, if if at 600 this equation x upon 2 root dt at 600, if it is equal to the x upon 2 root dt at 500, then the results will be exactly same. Right? Since the results are same, that is spatially they are exactly same. Like the if I'm talking, let's say this is a surface. So from the surface to whatever depth I go, I should find the same concentration. The value, whatever the depth I go, I should find the same thing. The concentration should be the same. So this is also the same for both the cases since we want the same diffusion result. So x is also same. We can cut this. 2 is a constant. We can cut this. So overall we can square both the side. So diffusion d into t at 600 should be equal to the d into t at 500. Now we can substitute the given values. Let's try to do that. So at d at 600 are 5.3 into 10 to the power of minus of 30 times time. Time is at 600. We know that it took 10 hours. It will be equal to the diffusion coefficient at 500. 500 is 4.8 into 10 to the minus of 40 multiplied by time, which is unknown, which is what we need to find. Let's try to do this. We'll bring everything on this side. What I will get 5.3 multiplied by 10 to the power of minus of 12, the whole divided by 4.8 into 10 to the power of minus of 40. So let's try to do this. If I simplify it little bit, it will be 5.3 divided by 4.8 multiplied by 100. This will cancel out. So let's do the division. 5.3 divided by 4.8. It will come out to be the 1.104 times 100. Now we need to remember that the unit of the time which we used in the at the 600. So that was hour. So here also the thing which we are going to get will be in hour. So let's multiply by 100. What we will get? 110.4 hours of time will be required. So the thing which was done at 600 in 10 hours, if someone want to do the same thing at 500, they have to go for the 110 hour. So we can see the huge difference in is there in this. So now what industry people will try to do, they will try to find that the how much energy it's this much taking and how much energy this one is taking. And based on that, they will uh, they will try to optimize their parameters. And that's how we have solved this question number 70. If there is any doubt in this question, please let me know. If not, let's move ahead to the question number 18. So now here, what diffusion path has the highest activation energy? So highest activation energy means that the one which is very difficult to occur. So which one among this? Lattice, surface, grain boundary, or dislocation? So among all this, which one will be having the highest activation energy? See, if I make a lattice, yeah, that's right. Option A is the right answer. That is the lattice diffusion. Because surface is a defect, we know, and the defect is having the higher energy. Again, the grain boundary is the same thing we can say, and the dislocation is again the same thing. Now, if we try to arrange the things like which one is having the highest energy, so the lattice diffusion is the one which will come first. Let's try to find the order. The next one, which one will be? It will be dislocation, grain boundary, or surface. D, C, or B. Which one should I write? What do you think, Zamility? After lattice diffusion, which one is the second one having the highest energy, activation energy? That is option D. Perfect. Dislocation density, dislocation diffusion. What will the next one? Surface or grain boundary? It will be the grain boundary, right? And the remaining is a B. So this is the order in which the activation energy is there. So the ease of movement, the ease of diffusion will be the opposite. Okay. So our right answer is option A. Okay. Let's move ahead. Let's go to the next question. Question number 19. And this is today's final question. This question is telling that okay, we have to match. We already did this part, I think. Yeah. Still, so you can directly tell me the answer. Lattice diffusion. Okay, option A. Surface diffusion is the one which is having the lowest activation energy, right? So the option B we will go with the
identifier junior assistant కదా వాళ్ళ
okay, option C, and then
Yes,
dislocation
PhD
diffusion will be
student.
the it will be the D. Right. Okay, that's great, Ramiredi. Let me ask you that do you have any doubt in the this particular week, which we week 7, before we wind up? If there is any, feel free to discuss. If not, then that's great. So these are the list of the questions that we have gone through today. Just have a look once. And if you feel any difficulty in any of them, you can let me know. Also, if you feel any questions about the last week, week 7, which you are not able to solve, if you want to discuss that, then also it is fine. We can solve it right now. If not, let's move ahead and we'll wind up the today's class. These are the list of the content that we have discussed today. So with that, our dot solving session for the week 8 is been over. It's nice to see you again, and let's uh, let's complete our today's class. Okay, then we ready. Bye bye. Yeah, thank you.